Hey everyone, this is Vladimir Jovanovic, and I am here to cover the next lecture in hypothesis testing and extend the stuff that we discussed with you guys on Monday. Okay, so there's going to be a couple topics that I'm going to cover. First are parametric versus non-parametrics, or a general review of what we covered previously. Then I'm going to go into detail about one sample test, two sample tests, paired sample tests, and then correlations. And so hopefully by the end of this, you will feel comfortable about choosing what kind of test statistic you need in order to get an accurate sense of what hypotheses you can test with your data. So, first, just to cover from before, parametric versus non-parametric. Parametric refers to distributions that have defined parameters like mean, variance, standard deviation, or let's say the number of turns to take or the probability of some event happening that helps determine how the distribution looks like. Usually these assumed distributions are continuous, and so they go typically from negative infinity to infinity, and they can have values like 0.3 repeating. Non-parametric ones don't have an underlying or assumed distribution, and if you plot it in a histogram, you shouldn't really be able to recognize it as any particular distribution, and especially so as a normal distribution. It shouldn't look like one. It's used especially so in ordinal data, mostly because that stuff isn't continuous and it is kind of weird to deal with. Ordinal data, good example are movie reviews, which can be 1 star, 2 star, 3 star, 4 stars, right? Each one we know in order how it compares to the other ones, but what it actually means, or what it means to be 2 stars away from something else, that doesn't actually really hold any weight, except saying what is the minimum, maximum, or what is less or greater than. So, as we covered, we do have one sample test. This is basically testing the hypothesis that given the sample or the number of the observations that you collected, that it comes from some particular distribution. And so what you get is a p-value, which tells you the probability that given a distribution that you would have gotten the sample that you collected. For normal data, tried and true is to go with the t-test. Non-normal, there's multiple ones, but two that I'm going to cover are Pearson's chi-square test and the one sample Kolmogorov-Smirnov test, or KS for short. So for the single sample t-test, this has already been covered by V, but just as a reminder, you have basically t is equal to the sample mean subtracted minus the population mean, and that's divided by the sample standard deviation, which is further divided by the square of the number of samples. The resulting t and the degrees of freedom of n minus 1 will give you a p-value, and then you will compare it against your alpha in order to determine whether you can reject the null hypothesis or not. So Pearson's chi-squared, where chi is the Greek letter for x, is a statistic that basically figures out that given the sample that you collected, that it comes from some previously defined distribution. What's nice about this one is, as long as you know what the distribution is and how to formulate it, then you can test chi-squared against anything. This stuff is also used a lot in comparing your models. You have a model of expected data and then the data that you have actually that you want to test against. One of the simplest ones or example that we can cover is basically trying to determine if a 6-sided die is actually fair. So there's an equal chance of 1 through 6 being rolled on any one dice. So we know what the distribution is for that, and we can roll a die multiple times and then test to see whether it actually conforms to this distribution. Basically what you do is you compare the likelihood of each category, which in this case the number that appears, occurring to the null hypothesis, which would be saying that it should be equal to the known distribution. Alright, so for the Pearson's chi-square test statistic, you need to take the sum of squares. So basically what that involves is taking the observed frequency of something happening and subtracting from it the expected frequency of what it should be doing if it followed the distribution, and then squaring that, adding it all up together. In the case of the fair die, what you have is an expected value of the number 1, 2, 3, 4, 5, or 6 being rolled, which are all equal. And then you have some observations that might be different from that. In the example here in the bottom left, you see red lines going horizontally, indicating the actual frequency obtained. And then we have that vertical lines representing that distance between the two. Once you add that stuff all up, you also get the degrees of freedom, which is n minus p, which is n the number of categories that you looked at. In this case for the dice, it's 6. And then p, which is basically the number of parameters needed to describe the distribution. In the case of the die one, it's actually 0, so it's 0 plus 1. So 6 minus 1 is going to give you a DF of 5. And then graphed is a chi-square PDF of 5. And with a DF of 5, and given the test statistic, you apply it there and see what value you get. And that allows you to get the probability and then figure out if you can reject the null hypothesis that the observed data comes from the distribution listed. Another non-parametric test is the Kolmogorov-Smirnov test, as mentioned before. In this one, it's actually similar to the chi-squared one, where we basically take the sample's probability distribution and compare it against another reference probability distribution and try to see if they're close enough together. In the KS test, there are two assumptions you're making: that the variable is at least ordinal, so basically there's some way to order the values that you collected, so it can't just be categories, and that the sample isn't normal. And basically what it does is it finds the maximal difference between the expected distribution and the sample. So in the image on the right, you have the expected distribution, which is in red, and the observed data, which is in blue, and then the maximal difference, which is indicated by the black double-headed arrow. That is what's actually used for the test statistic, and then the distribution I'm not going to go into. You can get the p-value and the actual rejection of the null hypothesis if it's low enough. So moving on to two sample tests. Basically this is a case where you have two groups that you want to test to see if they're independent from each other. Or another way to put it, the null hypothesis that the two populations have the same mean, or basically that both samplers are from the same distribution or population. It's basically all ends up being very similar in the sense that you're just typically comparing the means or some other value to see if they're really that different from each other or not. One example in neuroscience would be looking at the spike rate of a bunch of cells in two different parts of the brain and trying to see if they're actually that different in spike rate. Depending on the distribution of the two samples, it will help you determine which test to use. If it's a normal distribution, then you use the two-sample t-test. If it's not normal, there are two: the Wilcoxon rank sum test, or the U-test that I'll refer to, or the two-sample KS test. So for the two-sample t-test, you're basically dealing with normal distributions of data. There are different formulas dependent on the different scenarios of the samples, like if they're equal sample size and equal variance, but maybe different means. If they're equal variance but an unequal number of samples, or an unequal variance and then an equal or an unequal amount of samples. And t-test 2 is the MATLAB function, and there you can actually specify some of these assumptions, like whether the variances are unequal or not. You can actually go to Wolfram Alpha and explore this. If you type in Wolfram Alpha and in there type in two-sample t-test, you can explore putting in different values to see how that changes your test results. So this is just an image of that showing you basically, here's, two sample means and their sample sizes and their standard deviation. And basically then on the right you can see the null hypothesis that there is no difference between them, and then you know, what kind of tail test you want to take. In this case it's a left-tailed one, and the p-value is 0.111339. So if your alpha is 0.05, as in this case it is, you would not be able to reject the null hypothesis that the two populations actually are from the same or the same. So moving on to the non-normal tests, you have the U-test. Here you assume that you have equal variance and that it is a continuous variable as opposed to just being ordinal. So there are values like 0.1333 and 3.445 or something. And then the big assumption is that you have identical non-normal distributions, which is your null hypothesis. So basically what it does is it ranks all the values and determines if there's equally higher and lower values in both samples. It's great for non-normal data, and it's kind of easy to do. So I'm going to cover how you calculate this. It is not that pertinent for you guys, but it just might be an interesting way to get a sense of how these tests work. So basically what you do is you assign a rank for each value in the combined samples, then add up the assigned rank values according to the samples, and that gives you test statistic C, and then you use the U-test lookup table to figure out what the p-value for that is. So on the left we have two samples labeled A and B. A has 4 observations, B has 5 observations. So you combine them, both of them together, and order it. I put an underline under the numbers that are from A just to keep track of which one is which. And then you apply the rank labels. So basically you start from 1 and go up to the maximum value. So we have here 1 through 9. The underlines represent which of these values actually go for sample A and which one goes for sample B. The rank sum, represented by the letter R, for A is going to be 1 plus 3 plus 5 plus 6, which is 15. And for the rank sum for B, it's going to be 30. Now here, N is actually determined, N1 and N2 is determined by which sample has the larger sum. So here, B has 30, which is greater than 15, so N1 is equal to 5 and N2 is equal to 4. So then C is calculated by the formula below. Basically you multiply the n's together, do a bit of math on n2, and then subtract from that the rank sum of n2 or A, which is 15. So the resulting value is C equals 15. Then you need one more value, which is n1 times n2 minus C. In this case it's 5. And then you take the larger of those two, and that gives you your U-test statistic, or U-calc, which in this case is 15. Your parameters for the U-test are going to be N1, N2, and alpha. So in this case, you can see the U-test is equal to U of 5, 4, and 0.025. You go online, you can look up these tables, and in this case, the value is actually 0. So if U-calc is greater than that value, then you can safely reject a null hypothesis that these two values come from the same distribution. Moving on to the two-sample KS test, it's very similar to the one-sample one. Basically, again, assume non-normal samples and unequal variances from both of them, but assume that they are the identical distribution. So here you just plot the cumulative probability functions for both samples, basically the odds of any one value occurring, and then find the maximal distance between them, represented in black here, and from that you determine whether you can reject or whether you can reject a null hypothesis that they are actually the same. So then moving on from that is the paired sample test. In this case, you have independently paired samples, typically linked one-to-one with each other. Usually you see that with like before and after experiments or within subject experiments. For instance, having the spike rate of a neuron, then applying some type of drug to it, and then looking at the spike rate afterwards. And you want to see if there's actually, if the drug actually makes a difference. So in that case, what you do is you compare the two samples from before and after for the multiple neurons that you collected and see what happens. And typically what you end up doing is just a one sample test, but you just take the difference between all of the pairs instead of choosing one of the samples. The null hypothesis here is usually that the mean of the differences is 0, or basically that there is no difference in the change from one to the other overall. So first, a paired sample t-test. It's the same as the one sample t-test with n minus 1 as the degrees of freedom again. You basically take the difference of the paired values. So you take sample 1 and sample 2, which both have the same amount of observations, and just subtract them. And then you use that as your test for your test statistic. So moving on to the actual description of it, you can skip this part if you don't care too much about it, because you could always just put this in MATLAB automatically. But basically, let's assume that you have the neuron's average spike rate during stimulus presentation before and after a drug application. So H0, or the null hypothesis, is that the drug causes no change in the spike rate. And let's assume a two-tailed test in that. And let's say you found 5 neurons that you applied this drug to. So before, you have the spike rate 10, 15, 25, 45. And then for those same neurons going in order, afterwards you have 16, 14, 27, 6, 4. So the first thing you do is you just take the difference between them. So that's here, 6, -1, 2, 20, -1. And then that difference is represented as the mean of that difference, which is d bar, which is the average difference. Here it's actually 5.2. And then from that you subtract the assumed difference, which here it's just going to be 0. And then plug in the other related values, and you get a t. And then your degrees of freedom is just n minus 1. And then you get a p. So here the value is 0.8, which is way too high and does not allow us to reject a null hypothesis from this data set. The important thing to remember here is that this actually looks very similar to the one sample t-test. The only difference is that d bar has replaced x bar, and mu naught has been replaced by delta naught, which both actually end up being 0 anyway. So moving on to the non-parametric pair test. So basically here it's finding differences in the pairs, and you have to first see if the distribution is normal. If it's normal, you do the t-test and you're fine. It is also possible to get normal data from non-normal data if you're able to z-score properly or change your ratios on it, but typically you might run into some issues with that, so you can run these Wilcoxon signed rank test or the one sample sign test to do your non-parametric pair test. The Wilcoxon signed rank test is usually used. The one sample sign test might be, but it's one of the oldest tests. There are better ways of doing this stuff. So the Wilcoxon signed rank test, basically you have paired data as before, but it's not normal. You're assuming that the differences are continuous, which just basically means that it goes from -infinity to infinity. That's the possibilities. That the distribution of the differences is symmetric, so that there is equal amount of differences being below and above, and that the differences are mutually exclusive. Basically it makes sense that what it means to have one being less than the other, and then that the differences all have the same median. So overall, when you take all the values, the difference values should have the same median value. So I'm gonna go into detail about how to do this test. Again, you can skip this area just because it's not going to be that important. You can just plug in these values or plug in the functions as needed in MATLAB. But to do this, basically find the differences again, record the sign in one of the columns, and then record an absolute value of the difference. So basically you keep track of whether it was a positive or negative difference, and then what the actual value was. Then you're going to rank and give a rank label to all those absolute differences like we did before with the U-test. And then you're going to place those signs that you saved on those ranks. And then you get the mean ranks, and then you get the z-value from that and the z-test. It's actually pretty similar to the U-test. Moving on, there's the one sample sign test. It's one of the oldest tests out there. It basically assumes that if you have two samples from the same population, their differences on average would have the same amount of positives and negatives because they're roughly the same. So basically what you do is figure out the probability that you would get those amount of positives and negatives, and then compare that to what the expected value will be if it was equal likely chance of either one occurring. So again, on the left, this is the same data as before. You can skip this area if you don't need, if you don't care to go through the math. But basically on the left, same values that as we did for the paired t-test. Again, you have a difference of 6, -1, 2, 20, and -1. If you take the signs, that's going to be plus, minus, plus, plus, minus. The test statistic Sn plus is basically the number of positive differences, and here it's actually 3. And basically Sn plus is comparable to the binomial distribution, where n is the number of samples, which is 5, and p is the probability that it's all fair, which is 50%. So Sn plus is roughly approximated by this. You can imagine it that it's like flipping a coin. If both distributions are from the same area, then if you take the difference from the two of them, it should be about 50% chance that it's going to be above or below. So then you take the probability for the two-tailed test that Sn is greater than 3 and that Sn is less than 2. I'll go into some detail later if you have questions about that. And basically the p-value is 50%. So you definitely cannot reject a null hypothesis. But it is interesting to note that this is actually much lower than the t-test, which gave us 82%. So moving on from these tests of paired, two sample, or one sample, there's the f-test of equality for variances. I'm going to go into much more detail on this one next Wednesday, but basically sometimes what you really care about is the variance differences and not really the mean. So basically you're trying to test if there's equal variance. Or you care about the means, but you're assuming equal variance and you have a lot of populations to compare. It's not just two. For the cases above, you use the f-test, which is based on two random variables that have normal distributions. It's similar to the chi-squared in that it can tell you how well a model fits to the data, in that you take the expected values from the observed values, and from that you get an f-test that can just tell you if it's significant or not. And it relates heavily to ANOVA, which I'll be covering next week. So the next thing we have to discuss is two variable relations, or basically correlations. So just going to be recalling population statistics. Going to go over this just to help beat it into your mind. So there is a given random variable RV with some distribution. So let's say the binomial distribution, and from there you can get the RVs of 0 and 1, 0 and 1, 0 and 1, or something. So there's a random variable x that we're just going to refer to, and it has an expected value, e of x, which is basically what the mean is for this population. Variance is the expected value of x minus the mean squared, or the expected value of the random variable squared minus the expected value or the mean squared. Mu here is equal to e of x, or the expected value of x. So that's variance. Basically variance just tells you how much a random variable is deviating from the population's mean. And then the population standard deviation is just the square root of the variance. So given the standard deviations, all those values, sometimes you want to know, given two random variables, how do they relate to each other? Basically, how much does x and y change together? That is what covariance is, or how they covary. So COV, covariance of x comma y is equal to this thing, which basically is saying that if you multiply the two variables and subtract from them the two means multiplied together. That stuff we don't really interact with much. It's not usual that we're dealing with population level statistics, though. So what's more important for us is the sample covariance. That's typically what we're going to be interacting with and what you should be more comfortable with. So here you have the matrix Q, which is k by k variables. So let's say that you want to see the covariance for x and y. That's going to be two variables, so 2 by 2. So for any one of the comparisons of those two, it's just going to be 1 over the number of observations for them both, and then the mean subtracted from each of them, basically the variance, squared, and then summed together. So from the covariance of the population, you can also get the population correlation. So correlation is basically the description of dependence among random variables. And dependence here basically means when two random variables are not completely independent of each other. If they're completely independent of each other, they don't affect each other in any way. There's no pattern to how they behave when both of them are together, or correlation is equal to 0. So there's a value for this called Pearson's correlation rho. And this is the population level correlation for two random variables x and y. It's actually pretty simple. You just take the covariance of x and y and divide it by the multiplication of the standard deviations for x and y. If you get a rho of 1, then you have a direct increasing linear relationship between the two. -1 is a direct decreasing linear relationship, and as said before, 0 basically means it's uncorrelated. There's no dependence. They are independent from each other. So the sample correlation is something that you're going to be interacting with much more, and in this case you have paired data sets, and you want to know that in two given variables, when does one increase, and if it does the other increase in the same way? Does it decrease, or does it just go in different directions? So Pearson's R, from the same guy, is the sample correlation between variables x and y with impaired observations. So basically, if you took the, for instance, spike rate for one neuron and spike rate for another neuron as stimulus are presented, you can see if they're actually correlated, if they increase at the same time or decrease at the same time. So R is basically equal to this covariance stuff divided by the standard deviations at the sample, for the standard deviations of the sample. Again, it goes from -1 to 1. You can also do nonparametric statistical dependence that doesn't assume that you have some known distribution. So there's the Kendall-Tau rank correlation, which basically looks at the dependency of ordinal data. So in those cases, that, as I mentioned before, that's like movie reviews. You know which one's greater or less than, but it's not actually like real numbers where it's continuous. And then there's also Spearman rho, which is a nonparametric measure of dependency as well. Basically, it's based on monotonic functions, and those are functions where it's either consistently increasing as the x value increases, or consistently decreasing, and never goes back and forth. And here you can actually see a distribution of two variables, and their Pearson correlation, Spearman correlation. And as we look at it, our glance, we can see that there is a relation here, but Pearson doesn't pick up on it as well as Spearman, so it can actually be rather helpful, especially for nonlinear data. So, given that you have the sample correlation, sometimes you want to know what the true population correlation is for these two variables. So the Fisher transform gets that estimate of the population correlation given the R, or sample correlation, and N, the number of samples. Basically, it's a z-score, which is equal, the z value is equal to 1/2 times the natural log of 1 plus r over 1 minus r, the arctan h, which is just a MATLAB function you can type in. And then the standard error for that is dependent on just the number of samples. So z becomes the estimated rho, or the population correlation here. And then there's also testing correlation for significance. So the null hypothesis is going to be that the two variables are unrelated to each other, or rather that r equals 0. P then is a probability that the data, given the null hypothesis that they're not related, arose from that. So what you need for that, again, is just r and n, the number of samples, and thankfully this is actually very easy. You just use the t-test, and here t is equal to r over this value. The df is actually n minus 2 rather than the typical n minus 1 that we're used to. So let's say you have a correlation of 0.2 for the sample correlation, and n is equal to 100. So 100 samples and two variables that you collected, you got 100 of each of those. T is going to equal to 2.02, df is going to equal to 98, and the p for the two-tailed, I believe, is going to be 0.0461. So what we can say here is that we can, given an alpha of 0.05, that we can reject the hypothesis that these two values, which have a correlation of 0.2, are not related. So right here I put up a website link for you guys. You can test out how good you are at guessing correlations. So go to guessthecorrelation.com, make up a dumb username for yourself, and then start trying to guess. I have a high score of 9, so I think that's pretty great. I would like to see if anyone can beat that. It is surprisingly fun. And then finally, I just want to cover this for your own education and knowledge. If any of you worked in Excel, I'm sure you try to put it in, fit a line to some data, maybe in physics lab or something else, and you would get an r squared value. So how does the r squared relate to r correlation? So r squared is the coefficient of determination, and it's a number that basically tells you how well the model fits the data, or how well the line fits all the data points that you have. So basically r squared is that value that goes along with a line fit on some scatter plot in Excel. 0 means that it doesn't fit it at all, and 1 is a regression line fitting it perfectly. So obviously the closer to 1 it is, the better that is for you. So that's all the data that I want to cover with you guys. I apologize for taking so long to put up this lecture for you. A lot of the stuff that I went over as far as how to do the calculations is in this first link. It's a great PDF. The second link is actually a paper. It's actually related, directly related to the bonus question I'm going to be asking. It's only for 4 pages, very short. You don't even have to read most of it. But I recommend you just perusing through it so that you have a better sense of how to approach the bonus question. So thank you for listening. I appreciate it.